Alright, so now I have an exploded view of my structure. The next thing I need to do is write out the slope deflection equations for each member. And my members are here. This is member AB, member BC, and member CD. And I'm going to have 2 slope deflection equations per member. So let's start with member AB. So I've written the generic form of the slope deflection equations here with MIJ. You might see a different textbook. They might use, instead of IJ, they might use NF, AB, near, far, whatever you want to do. But this is the general form of the slope deflection equations that are used, and I have it here as a reminder of how or what to do. And so the first thing we're going to do is write out the slope deflection equations for member AB. And if you recall the frame from before, just to give you a quick reminder, it looked like this. And so for this equation here, that first slope deflection equation, MAB, would be 2EI AB over the length of AB, 2 theta A plus theta B minus 3 psi AB, which is the chord rotation, plus FEM, the fixed end moment at A. And then you'd have, again, 2 equations per member. So for member AB, you'd have the MBA would be 2EI AB over LAB, 2 theta B plus theta A minus 3 psi BA plus FEM BA. And there are things here that we know already. And just going to take a quick look at these. Here, I know that EI is constant for each member, so I really don't need that notation or the subscript AB because EI is the same in this problem for every member. So I'm just going to erase that AB. See ya. And I know that the length of member AB is 18 feet, so I'll just substitute a number there. Boom. And if I look at the boundary conditions, I know that the rotation of joint A is going to be 0 because it's fixed. So theta A is 0, 0, 0. And now what's left is this chord rotation, psi AB, or psi BA, and these fixed end moments. Now, we'll start with the chord rotations, but the chord rotation is associated, in this case, with the sidesway. Because we have an unbraced frame, we want to know what is this rotation that my member AB is going to experience. And now we may not know the displaced shape of this frame, but we know that point B will move to the right. And because we're neglecting axial deformations, point C will move the same distance to the right. And if I just connected where my joints are after it deforms, I would have here this shape I would have. And again, this is not the displaced shape. It is just kind of the chord rotations that my structure are going to experience. And this distance right here, we're going to call delta. And this delta is the same for these nodes or joints B and C. Boom, right there. And if I look at member AB, I would say that the chord rotation from the point of view of A is that member AB rotated clockwise, and that would say that this chord rotation, this right here, this rotation, I would say that psi AB, because it's clockwise, is considered positive, is equal to delta over LAB. And then again, if I look at from the perspective of point B, here this was the original, let's say the original position or the straight member AB. And if I look at it from point B's perspective, my chord rotation was like this. And that would also be a positive clockwise rotation. And psi BA is equal to also delta over LAB. And again, these units are in radians. And here, shoot, all this tells you is that psi AB equals psi BA. So, whoa. So, you know what? I'm just going to call this over here psi AB. Now I want to determine the fixed end moments of member AB. And the fixed end moments, it's a condition where everything is fixed. Okay, the supports are fixed. What are the end moments on a fixed beam? And if you Google fixed end moments, or if you look on the inside cover of your textbook, you'll see all these diagrams for fixed end moments. And here for member AB, because we have loading here, a uniformly distributed load, the fixed end moment diagram that you probably see would look like this. And my fixed end moments here on the left side would be WL squared over 12. And here also WL squared over 12. If you recall, my beam is going left to right just as before. So this side would represent joint A here. And the fixed end moments at end A, or FEM-AB, would be this WL squared over 12 counterclockwise, which means that this is negative WLAB squared over 12. And the fixed end moments at BA would be clockwise, and therefore these would be positive WLAB squared over 12. And if you look at the other members, I've got no loads there, so that means, hey, I've got no fixed end moments for the other two members when I do the slope deflection equations for them. And if I go ahead and calculate this WLAB squared over 12, that FEMAB, if I plug and chug, is going to be negative, and this is negative 162 kip feet, and here FEMBA is going to be positive 162 kip feet. And those are my slope deflection equations. You know, for here, I don't need to substitute this delta over L yet, unless I want to solve for delta directly. But I can leave this psi AB as an unknown. What I want to prove was that the psi AB and the psi BA I had written here previously are the same for this member. And so if I rewrite this in a more simplified form, and here are my two slope deflection equations for member AB. Done. Now we'll go on. I'm going to repeat the process for member BC and member CD. And notice in member BC there's no chord rotation, so the psi is going to be equal to 0. Hey, all right, check it out. And in this case, the length of member BC is 24 feet. And I keep it EI. I didn't call it EIBC because EI is the same for all members. And then the chord rotation in this case is 0. And I have no loading on this member, so fixed end moments are also 0. And what I will be left with are the following two equations if I do some reduction here. And these are my slope deflection equations for member BC. And now, last but not least, member CD. And in this case, if I go back and I look at that drawing I had before, first thing to note is that my rotation at point D is 0 because it's fixed. Yay. And because member AB and member CD have the same height, recall it from the perspective of joint C. This is a positive chord rotation right here. So psi CD is equal to the same delta over LCD, and psi DC is equal to delta over LCD again. Since LCD is equal to 18 feet, just like LAB, in fact, all these chord rotations are the same. So I'm going to go ahead and I'm going to remove the subscripts. So instead of calling it psi AB and all that, I'm just going to call it psi. Psi for psychology, or Gangnam Style, right? All right, shoot. Again, I'm going to also remove that boom, boom right here. I know that LCD is, the length of member CD is 18 feet, and the rotation of point D is 0. Bam. Since I have no loading on member CD, 0 fixed end moments. Hey, and now when I go ahead and rewrite this in a simplified form, it's going to look like this. And here are my slope deflection equations for member CD. Woo!